Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. And in this lecture we will be actually looking into the front end circuits for qubit readout and especially on spin qubits part. So, the outline of this talk is basically we will look into qubit readout front end circuits, look into spin to charge conversion because qubits are primarily into spin and therefore, one should have a methodology of converting the states of the qubits onto a corresponding charge which can be extracted from the qubit, and then the charge therefore be a function of the spin of the electron in the spin qubit. We will also look into SPAD micrographs and then look into noise cancelling low noise amplifiers for small signal analysis. Now, this we have already done, but just to refresh your memory, primarily your qubits are placed in the quantum processor part. So, this is your area where your qubits are placed, right, and these qubits are effectively in around 4 to 10 millikelvin range, right, somewhere around 4 to 10, sometimes goes up to 20 to 100 millikelvin. So, if we have an optical methodology of detection, then we use an optical waveguide here which drops into an avalanche photodiode APD, which we have already studied earlier. That goes into an amplifier, low noise amplifier, which does a readout circuitry. Then it goes to a TDC, time to digital converter, followed which digital output is put at this particular point, and then they are used to control the demux here, right. There is another methodology by which if you go, it is directly through a low noise amplifier, then a mixer is there and you have an ADC, analog to digital converter. So, using that also you can have the digital control. The digital control is done either by an ASIC or an FPGA board. So, basically we are trying to convert these fragile quantum states, which are why fragile, because if you do a small amount of variations in their ambience, be it temperature or magnetic field or an external microwave source, they tend to change, and therefore, basically the conversion of the fragile quantum states into measurable electrical signals is what is required when we design a qubit readout circuitry for front end circuits. The various challenges which you face is of course fidelity, right, and speed, and of course there are cryogenic constraints, right, cryogenic constraints in the sense that the power budgets primarily. So, we will have constraints on power budgets to a larger extent, and therefore, maintaining the temperature somewhere around 1 to 4 Kelvin in the readout circuitry is a rather, if not an impossible task, is rather a difficult sort of task to maintain. So, this is the basic block diagram of any readout circuitry, and where we want to convert this into this quantum qubits into its corresponding charge. So, now we will look into the spin to charge conversion issues. Now, basically we try to change or try to convert the spin state of electron into its charge configuration, right, and this is done via what is known as a poly spin blockade, right, and then this charge signal is sensed by charge detector, right, which is a single electron transistor, and using that what we do is that we are able to detect the amount of charge. Now, please understand that the charge detector or the single electron transistor output signal is relatively very weak, and its signal flow is around microvolts to millivolts, but typically around the microvolt range, right. What does the low noise amplifier do while sitting at this cryogenic state is it tries to amplify the signal, but tries to keep the noise to the bare minimum, and that is what is written here, that it amplifies the signal and it tries to minimize the added noise. So, whatever added noise is coming, be it anyway thermal noise will be very small, but you will have other type of noise which will be added to the signal, because of which you will have always added signal to noise ratios will be always compromised. So, the low noise amplifier does what is the low noise amplifier tries to basically tries to amplify the signal and minimize the noise floor. Now, while doing all these things is the main issue which one needs to be concerned with is that the information stored in the qubit is preserved, right, and especially when you make it when you make the transition from a lower temperature to a higher temperature stages. Because if you remember in our previous discussions, previous lectures, we had shown that the information is carried from a relatively a very low temperature to a relatively high temperature, and there are certain stages through which it goes. So, you need to be very careful about that the information does not get lost or does not get sort of you do not put a wrap around it, and we are not able to get the actual signal or actual value of the charge at a later stage. So, these 3 things or 4 things you should be aware of in terms of when you do a spin to charge. So, basically spin to charge primarily means that the spin state is now being converted to a charge state, and since charge is the only thing which can be actually, so basically charge, which is basically either in form of voltage or current, you will be able to extract the information. Now, let us look at the mixer and filtering, right, because if you remember we had told you that there will be a mixing here and a filtering also available to us. Now, because you need to down convert your signal, right. So, what you do is that you amplify the signal, the amplified signal is then mixed with a local oscillator, which is an onboard local oscillator, another a challenge because typically local oscillators will have very relatively higher power budgets. So, one needs to be very careful how you design your local oscillator on chip at such a low temperature, that needs to be found out. And for frequency downscaling, you mix the amplified signal with that of the local oscillator. So, that is what written here, that local oscillator for down conversion frequency, right. What does filtering do? So, mixer is able to mix this amplified signal with local oscillator, then it passes through a filter stage. Filter stage is responsible for removing all various components of noise and unwanted signals at a particular band of frequencies. So, for a particular band of frequencies, the filtering action will be able to remove those unwanted signals, keeping my signal to noise ratios higher and higher. So, the output of filtered out of the filtering will be primarily analog signal, but devoid of any unwanted components or unwanted higher order harmonics in the signal or even noise in the signal, right. So, we have been able to do things, we were able to down convert it and remove the noise, and then we send this to an ADC. So, you see I have a this is a, and then we pass it through an ADC. ADC, as you all aware of, is responsible for converting this analog to digital conversion, right. And these are very high resolution ADCs which you assume, and they are primarily high, not only high resolution, they are primarily of high speed digitization, and they are generally required for a single short spin qubit readout, which means that you do a readout by using a single pulse of wave, either a microwave pulse or a photon pulse in order to read out the circuitry. The output which, so the ADC output will be a digitized output, and then they are send it to an FPGA board or an ASIC board, which is this one here, right. And then the digital signal is processed in real time to determine the Q state. So, primarily this double shaded arrow which you see here, this one is primarily responsible for basically letting the digital control here talking with the external world here. So, this is the external world where you have a qubit control to be done. So, what we have learned out of it is basically that you do mixing and filtering, you try to do it. Once you have done mixing and filtering, you do an ADC and lot of digital converter followed by an output with this digital control. Now, let us look at poly blockade and charge sensor. Now, as you are aware, a spin qubit carries a state, either it is spin up or spin down state, right. Now, direct measure of spin is obviously very difficult, because it is such a micro level calculation that it is very difficult for any hardware to find out the state of the spin, whether it is clockwise or anti-clockwise, right, spin up or spin down respectively. And therefore, that is the logic behind conversion of spin information into a charge state, right. And that can be, and since let us say spin up, right, spin up, or counterclockwise methodology is referred to as, let us say, Q1 state, and spin down or clockwise direction is supposed to have spin state 2. So, at least by looking at the, if you have these spins up and spin down states available to us, its corresponding charge value is Q1 and Q2, and therefore, by looking at these values of Q1 and Q2, I can do a back propagation and predict what is the value of the spin state. and basically this is a quantum Pauli spin blockade or tunneling phenomena based on which are there. Now show you an example of what spin blockade is all about. So if there are two electrons which occupy a quantum dot, right, and they consist of certain spin configuration, then certain spin configurations are prevented from tunneling out of the quantum dot while others allow tunneling, which means that it is something like this. If I have in a very simple manner, let us suppose I have a filter where my only spin up allowed to go up. Now let us suppose I have multiple spin up spin down states and then I let it pass it through this filter, then only spin up parts will be crossed through and spin down parts will be blocked. This is known as a Pauli spin blockade. So depending upon the state of the spin, certain states are allowed to move through the filter into the external world and certain states are stopped in the certain state are stopped in the filtering world by doing filtering. Now and that is what is written here, that they allow certain tunneling to occur, and therefore the difference in the tunneling ratio or the tunneling leads which we get, and that to a detectable change in the charge configuration. So if a spin up state as I discussed with you is Q1 and spin down state is Q2 and there is a substantial difference between Q1 and Q2, then I can a priori predict what will be the value of the spin depending upon which charge Q1 or Q2 is highest, right, and therefore I can predict the charge configuration in a much better manner in this case. Now let's look at the graph. So what we have plotted here is basically my IIP3, right, and this is basically input referred third order intercept point versus the frequency of the main tone. So I have multiple tones, I take the frequency of the main tone, the main basic one, second harmonic and third harmonics are rejected and I process the frequency with respect to IIP3. And the second one is IIP2, second order intercept points are generated with respect to frequency, and for both the cases we are comparing a 300 Kelvin case with a 4 Kelvin case. So 300 Kelvin is the room temperature and 400 Kelvin is the cryogenic temperature which we are referring to. So typically at 4 Kelvin, right, if you look properly, both this and this, both IIP3 and IIP2 shows approximately 10 dB lower value as compared to 300 Kelvin for 4 Kelvin, which means that lower IIP values mean relatively a worse linearity at cryogenic temperature. And this is a major problem which you face when you design low noise amplifiers, any frequency dependent issues which you want to design in a readout circuitry. What has happened is that as you go on reducing the temperature, in a sense the non-linearity issues becomes much more prevalent, right, and therefore worse linearity is obtained at lower temperature which is around 4 Kelvin range temperature, you will have worse linearity. If you look very carefully, the minimum value of IIP3 difference is somewhere here, right, which is around, if you look, 40 around 10, right, and at 100 megahertz the difference is approximately 20, this one is 20 dB and this one is approximately 5 to 7 dB. So the average value what they have found is around 10 dB which you are getting. If you similarly, if you look at this curve here at 40 and 50, the difference, average difference is about 10 dB. So 4 Kelvin is 10 dB lower as compared to 300 Kelvin, and that adds to nonlinearity, which when there is a nonlinearity, then typically that nonlinearity increases the output noise also of mixer, low noise amplifier and so on and so forth, which are basically frequency dependent component in the design. So this is the spin to charge conversion concept which we gave. Now why, let us look at why this sort of thing happens in low temperature. Now at 4 Kelvin obviously the amplifier has a higher gain, right, that we have seen earlier also, but Vg minus Vt is actually reduced, much reduced, because what is happening is that Vg minus Vt is the overdrive, and what happens is at the reduced temperature this threshold voltage starts to rise up, and therefore the difference between Vg and Vt starts to fall down, right, and therefore your overdrive voltages get reduced drastically. When the overdrive voltage gets reduced drastically, it basically worsens the nonlinearity to a larger extent. So, that is the main reason why we get heavily or a worse nonlinearity at 3 Kelvin or 4 Kelvin as compared to 300 Kelvin. However, there is a sort of a optimization which we need to do, because at low temperature, which is 4 Kelvin, you tend to have a much reduced linearity, worsens linearity, but at the same instant of time improves noise performance. Now, your noise performance is better and your linearity becomes also larger, which means that non-linearity increases, it reduces linearity, non-linearity increases. So, the cost you pay for improved noise performance is paid by reduced linearity as well. Now, if you want to convert a spin to a charge, which I displayed to you in the previous slide, you will see that the amount of charge which is stored in the output side is very small, extremely small, right, and therefore, you need to amplify that charge, or you need to convert very early from charge to voltage or something like this. And that is where the cryogenic amplifier comes, which boosts with low noise, but linearity still matters to avoid distortion for multiplexed readout. So, if I have a multiplexed readout, I need to ensure that for all the readout outputs, your noise elements are reduced to the bare minimum, right, and therefore, the cryogenic amplifiers helps you to do that. Okay. So, let us look at the various other concepts here, and this is basically noise cancelling LNA, a low noise amplifier from small circuits, and as you can see, this is the source resistance RS here, this is the input source voltage, sinusoidal voltage which we insert, this is my feedback resistance here, this is the capacitance which is available to me, and this is basically an inverter with a C load available here. As you can see, this, if you pass this Vs through Rs and Ca, this tries to make my M1 go on whenever the voltage at this particular point, say X, exceeds the threshold voltage of M1 and M3, right. When M1 and M3, let us suppose the threshold voltage of Vs goes above M1, M1 switches on, and then it tries to pull this voltage down to the ground, and therefore, M5 switches on and M3 is still off, and my output here goes to, let us suppose, VDD, which is the output voltage. Suddenly, when the voltage here exceeds even that of M3, then M3 switches on and there is a pull down path, and the voltage goes to 0 in the output side. Now, what does a noise cancelling no noise amplifier is designed, and for spin qubit readout, and it enhances weak signals from charge sensor while obviously suppressing the input referred noise. All your input referred noise almost go to 0 in that case. Now, if you look at the key components of the sensor, let me just quickly go through it. Yes. So, the key component of the sensor, if you look, one is the input signal source, Vs is the input signal source, right, this is Rs is the source resistance, right, Rs is the source resistance, and this represents the charge detector output impedance. So, when you are detecting a charge, there will be an impedance attached to it. So, this Rs is the equivalent impedance seen at the output. M1 is the input transistor amplifying the weak qubit signal, M1 is the qubit signal which is amplified, and RF, Ca and Cb are basically the feedback and coupling element which are used for noise cancellation as well as for impedance matching between the input and the output. And M3 and M5 are output stage of a transistor which is driving a load which is C load. So, my C load output load is given by this quantity load, and this is this inverter drives this load by an external pulse which is given by Vs. Okay. Now, let me come to a noise cancelling LNA for small signal analysis, the same thing we will continue. So, what does RF do is provides a correlated path for the noise generated by M1. So, any M1 generated noise does a feedback loop, and the output which is this here, the noise contributions cancels while the signal is preserved, right, and therefore, it improves the signal to noise ratio for determining the state of or distinguishing the spin states. Now, spin to charge conversion, as I discussed with you, will always take place in the order of microvolts to millivolts range, and enables high fidelity single shot spin qubit readout. This allows you for a high fidelity single qubit shootout. So, how do you because this is important, because how do you actually try to find out the aspect ratio of the inverters of all the transistors here will determine how far amplification can be carried out for spin qubit readout circuitry, correct. This is typically of the order of few microvolts to millivolts, tiny signals are available here. Okay. Let me come to the next one, which is basically the quantum readout for using APD. As I discussed with you, there are two types of readout circuitry. One is through avalanche photodiode, as I discussed with you, and then is an amplifier section, which is basically through a cryo-LNA. Cryo-LNA we have already seen in our previous discussion, but avalanche photodiodes does what? It is basically in the optical domain. Spin qubit readout circuitry generates very weak optical signals. These optical signals are went to an APD. APD is an avalanche photodiode where there is a carrier multiplication, and so each photon comes and you have an electron hole pair generation takes place, which further generates more and more electron and hole pair, and therefore there is a sudden surge or a sudden spike of charge which you see after the APD, after the avalanche photodiode. After that it goes to an amplifier, basically an amplifier which goes through a typical cryo-LNA, and as I discussed with you earlier also, it maintains low added noise and boosts the signal, the output signal, SET signals, right. So, this output of an APD will go through a set, SET will change the optical to, we will have charge based output. These charge based output will be giving you a very microvolt order range of voltage, and then you send it to an amplifier which adds low noise and preserve the qubit readout fidelity. Now, let us look at the TDC here, and this converts this one. So, I have sent it through this and now we are at this stage TDC, and this converts all the analog pulses which you get from the output of an amplifier and into precise digital timestamps. So, you will have timestamps available, and these are very precise digital timestamp depending upon the analog pulse which you get. So, basically the sampling is done in the time domain, and you can actually sample the output, and those sampled output will have digital timestamp attached to it. Advantage, high resolution measurement, right, and that is why qubits are preferred over your traditional ADC structures which we do otherwise, but typically TDC is much more high resolution management of the qubit state transition. So, if you look at the flow of the data or the structure, then we first we go ahead and do the spin state, right. The spin state converts from spin to charge or a photon. Photon means if you are doing an optical, it is photon, if you are doing in the charge base, then spin to charge. Conversion takes place, then you do an APD detection, which is APT, and then AMP, TDC and digital readout. So, this is the typical flow of readout circuitry when you have optical domain as the one which is there. Please ensure that while you are designing this, you ensure that excessive noise is not added and the signal does not degrade as you start manipulating the signal right from the quantum processor up to the digital output, right, and that is very, very important as far as fidelity of the signal is concerned. What are the benefits? These are all single shot spin qubit readout, and they give you a very, very accurate sort of timing information for the spin qubit. Now, let us look at the SPAD micrograph, right. This is a single-photon avalanche diode, SPAD, right. So, single-photon avalanche photodiode means it is so sensitive in nature that even a small single photon can actually generate a large amount of avalanche current through the system. So, you have a PN junction diode, these are all fabricated at 180 nanometer CMOS, has been taken from the source which you can see at the bottom of the slide here, and these are taken from single-photon avalanche photodiode SPAD, which is fabricated at 180 nanometer CMOS. The diameter is approximately 12 micrometer, which is quite a substantial amount. You increase the area, depletion area, and that injects heavy avalanche current which is slows, right. Now, SPADs actually are responsible for detecting individual photons by avalanche multiplication, and they are very, very critical for all your weak signals from quantum devices. So, when you have very weak signals coming from quantum devices, these SPADs help you to increase the level of the current to a larger extent. Sudden increase in the current you want, this will provide you, which means that a single photon will give you a large chunk of charge in the output, and that is one of the advantage which you face while you do a quantum processor. Now, DCR is basically known as dark count rate, right, and this is basically whenever you do not have any photon falling into the SPAD, If you have still some current flowing, that is basically known as a dark current. With no photon present, you will have the dark current available to you. Now, if you see the dark current rate on the x axis, number of dark current per unit time and the bias given here, you see as you go on reducing the temperature from 300 Kelvin down to 77 Kelvin. So, these ones are for green and this one is for SPDED. There are two types of SPADs we have taken, one is a green SPAD and another red SPAD, but nonetheless as you reduce the temperature, it is seen that the DCR actually starts to fall down. So, when you are operating at 4 Kelvin, your DCR at excess bias of 1 volt will be very small. That comes to your rescue as a designer, because the amount of offset you add to the actual design should be very small in this case, right. And this is the graph showing for excess bias, means the bias which you are giving in the reverse side, and you progress the DCR on the y axis and you process the excess bias on the x axis, and you do have the variation of temperature on the for these graphs. And general scheme of thing is that it starts to reduce, the dark current starts to reduce at much lower, which means the noise is relatively small at very low values, right, and that gives you a very low count of DCR. As I discussed with you just now, the DCR decreases significantly with the lower temperature, especially at cryogenic temperature, and close to 4 Kelvin. It helps us to find out that it is essential for any spin qubit readout compatibility. It becomes much easier to handle both the SPAD and at lower temperature my DCR value is relatively very small, right. So, this is what we have learned about the SPAD micrograph here. Please understand, its active area is pretty large, which is around 12 micrometer, and this is majorly used for the purpose of detecting single photons when you have a photon way of detecting the output. So, let me recapitulate what we did during this lecture. We learned about the basic idea of SPADs, right, and how the DCR varies with respect to temperature. We looked into the meaning of SPAD and DCR, its functionality. Then in the previous part of it, we looked into the various readout circuitry and the various block diagrams and its functionality. We looked into its functionality, and we also looked at various optimization techniques for getting the best SNR in the output, right. With this, I think we will stop here today, and thank you for your patient hearing. Till we meet next time, goodbye.